In a car park in upstate New York, a couple is sitting in a car in front of a restaurant. They had the wedding anniversary reservation, but no appetite. And their eyes are red and swollen. They've been crying all night. In the back seat, there's a little girl. It's their first. They're staring at a science presentation on their phone. Baby, they've already cured it in mice, he says. How hard can it be to get it into the brain? I mean, they've got the package. They just need to get a cab and deliver it. The day before, their neurologist had told them that their newborn had a devastating disease, that she will never be able to walk or talk, and that she will most likely suffer seizures throughout her life. He says, there are diseases that we can cure, and there are diseases that we can only manage. This is the latter. CDKL5 is, as we know it, incurable. And it's very tempting for parents to launch their own attempt to find a cure, but I would advise against that. I think you should focus on growing your family. As you can imagine, I didn't follow that advice. There was Anna and I sitting in that car with our daughters here now. I'm here to present the roadmap to make DEs tractable and attractive. We'll see what kind of job I managed to do of that. I think this problem in general tends to be framed as how can you make a patient population of a few hundred or a few thousand attractive to the industry? When it comes to CDKL5, and I CDKL5 almost exclusively, so that's going to be the focus. I think we're in a fairly good position in the sense that we can approach this disease from the point of view of a classic gene replacement therapy or protein replacement, or small molecules. We've found ways of upregulating a signaling gene. I don't know if you're all familiar with CDKL5, we're going to hear more about it. And further ahead in the future, we can perhaps look forward to sort of universal gene editing approaches as well that can edit larger chunks of DNA. Another approach that you're all probably very familiar with is this idea of being able to group different DEs together. We can focus on different pathways, the neurotransmitter pathway, metabolic pathway, growth factor signaling. Some of these pathways are shared between different DEs, like FOXG1 or RET, or like Lundbeck and bexicaserin that you can see out here. Found a way of targeting the same serotonin receptor. Or you can focus on other aspects. Ultimately, well, you can also probably do an X-ray activation and focus on genes that, or diseases that are all X-linked, and then sort of cover that. All this to say that you could group a number of them together. You could possibly also, maybe we're lucky in the sense that depression also shares some of the issues with microtubule dynamics that CDKL5 does. And we also see that there is an overlap with calcium channels in Parkinson's. All of this is, yeah, that's it really. That's how you solve the problem. So thank you very much for coming to my TED Talk. Well, the issue really is that for CDKL5 we have hundreds of disease-causing mutations, and there is a varied distribution of these mutated cells throughout the body, either due to mosaicism or X-ray activation skew. We have examples of twins that have the exact same mutation that have totally different presentations. And I mean, I am no expert, but the question is, can you actually address the root cause by grouping all of this together? We're not alone in that challenge of making an N of 1 attractive to the industry. A few times a year, Ultragenics host this extraordinary event called the Rare Boot Camp. It's a very generous event, and it brings together parents like us who are desperate to find a cure for their children. I've been a few times, and the first time I was really overwhelmed by the gravity of the situation for some of these parents. There could be the cases of really one child diagnosed in the world, or the time is ticking, and you know, they have a few years to live. So in that context, CDKL5 is a lucky disease, or we are lucky because we have forces like the Lulu Foundation who's with us here today. We have patient registry, we have IFCR, we have mouse models, we have all these different things, which a lot of the other families or diseases don't have. So, and we have Ultragenics is also working on a therapy. So the thing is, even though we have those promising things, at the end of the day, we're in the same boat, because for our daughters, nothing has worked. So regardless of how lucky we are, we really have no meaningful treatment. And I have to be honest, I didn't go to the Rare Boot Camp to learn about rare diseases. I went there as an undercover agent to figure out, where's the cab? Like, you have the package, how do you get it there? And, so I managed to get a one-on-one. By the way, I recommend highly going to this event. Any parents, it's extraordinary. I managed to get a one-on-one with a scientist, who happens to be the scientist from the car park. And it became clear to me that it is a huge problem to get a cab if you need 50 billion cabs in the same day. Add to that the risk itself, the financial risk, the regulatory risk. And it was clear that the pharma industry is moving at a different pace than our children. And risk means something very different to the industry than it means to us parents. And let me talk a little bit about risk and urgency. And I just want to, you know, we're all here, we know what epilepsy is about. So I will, this is every night in our household. You've seen these things, so it's not novel to you, I hope. I wouldn't normally show it, it's pretty harsh. CDD is not considered a high-risk disease in the sense that it's a neurodegenerative, or that there's a high mortality rate, but that's actually not the reality for us parents. Every week on our social media groups, there is a child that gains their wings. And whilst it may not be that fatal, it's so debilitating that it's up to us caretakers to make sure that they survive. And so it's not necessarily just their mortality, it's our own that is at the top of the mind for a lot of us parents. So I can't sit around and wait for the industry to save her, so what can I do to accelerate meaningful treatment for my daughter? So that's what I came away with. So the fastest way to meaningful treatment, well, a few words about me. I'm sort of a normal guy. I used to just code. So I'm a software engineer, and I understand code very well. And in code, whenever you have a bug, you need to create a platform, a test harness, so you can replicate the bug and then try to solve it over and over again. And as far as I'm concerned, my daughter has a bug in her biocomputer, in her BIOS. So we need a system for rapid iteration and different possible solutions. And that is how CURE5 was started. In 2023, we teamed up with Lily Haas, who's not here today, but she also has a daughter with CDKL5. She's a force of nature, like a lot of parents. They are to be reckoned with. And these are our little girls. This is Margot and Sienna. And in 2 years, we've been able to establish a pipeline of 9 IPC lines with Boston's Children's, out of which 4 are already used in labs worldwide. We've done AI-powered in silico drug screening through nose swabs. I will talk about the next two projects in greater details because they're underway. We're trying to do drug repurposing through high throughput screening. And we're also actually working on a new CDKL5 specific molecule. So what is the fastest way? Well, so, you know, my engineering brain goes, there's a lot of unknown things about this disease, unknown pathways, downstream substrates, unknown interactions. We don't know so much about different cell types and how specific it is to different cell types. There's a whole host of things we don't know, in spite of all the research and wonderful work that's gone into it. Likewise, when it comes to the drugs that are being used, don't quote me on this, I can quote ChatGPT should you want to. So 20% of drugs are more or less unknown to us in terms of the accurate mechanism of action. So what if there is a blessing there? What if there is an overlap in what we don't know about CDKL5 and what we don't know, even perhaps what we do know in the available and safe drugs out there? In that overlapping area, maybe there is something. So to that effect, from these iPSC lines that we've generated, we have started to grow organoids. Yes, they will be sort of not full-fledged complex organoids, and more spheroids to be suitable for the type of screening that we're looking to do. Because what we want to do is to have lots and lots of these organoids and feed them through this sort of a machine that can read the electronic signature. It can essentially see the calcium transients, which is sort of a proxy for a seizure. And what's interesting is that you can get a readout of how those pulses happen and compare them. So we see a healthy organoid at the top, and we see a very distinct pattern when it comes to a red organoid in the middle and the one CDD organoid that's happened before. And I'm sure others are doing this as well. But then the idea is we've got our test harness, like a programmer, we've got the thing, so that now we can then try all the approved drugs on that platform. And if there is something that then normalizes that signal, we can reduce the number of candidates, and then we can do follow-up screenings that's to say look at cell morphology, different readouts, EB2, there's all these endpoints that we could look at and end up with a de-risked therapeutic candidate that might go to clinical trial, or even faster if clinicians are on board to get an off-label prescription and actually try it straight up because it's a safe and known drug. And very excitingly, this is the Sienna line, and we affectionately call it the Cyborg. And then we got the Margot line, which we called the Borgonoid. And yesterday, we just got the first recording of the Margonoid line. So these are 4 weeks old neurons grown in the dish that can capture the synchronized patterns in the brain. So that's very exciting, but it doesn't stop there. We're hopeful that this sort of project will then generate so much information that we can gather that and feed that into the latest NVIDIA AI model and get a disease map or information about downstream targets of this gene. So if you do the I'm not going to go into detail, I don't necessarily understand it, the RNA-seq data, you can extrapolate and see what other genes are dysregulated, and then establish something on the map. And from that, we can then start to generalize. And you can perhaps then look at other targets that we didn't know about. So all in all, it is an N01 to start with, but then we can generalize to the broader public. And you know, this sort of platform can be expanded on. Maybe it even lends itself to patient stratification. We don't know a good way, as far as I know, of who is a responder, but maybe there is information or data in there that can help us figure out what drugs work for what children. So it's hopefully very useful. That approach was agnostic in terms of that's just the fastest way. We don't know it. So almost ignorance is almost a gift in that scenario. But we're also collaborating with a Dublin-based company called Neuroscience, and the lead is that CDKL5 by and large seems to be a disease related to the cytoskeleton and the microtubules. And we found a way in which one of the downstream targets is that's normally opened up by CDKL5 could be opened up by a small molecule, pregnenolone methyl ether. And the hypothesis is, yes, that's the hypothesis. We haven't found other ways of substituting CDKL5 in terms of phosphorylation. This is getting technical, but this is an example of possibly there might be other ways to substitute some of the downstream effects of a disease like this. And, you know, this was not discovered through blind screening. This was discovered because Masi Bianchi has got a history of studying this molecule, but it could happen, right? It's the kind of project that could happen. And we've already got data from mice that is very promising. Knockout mice treated with this molecule are already showing signs of normalizing their behavior when it comes to open field and marble burrowing. And finally, when it's dissected, the acetylated alpha-tubulin is an established endpoint for this disease, and it's also showing normalization there. So all this to say, I suppose the key takeaways for me is, I know there's a lot of academics pursuing research. Don't let the quest for knowledge be an obstacle to getting the treatments to patients. First, we need to find something that works. Then we can figure out how or why it works later. And I would also say to clinicians, maybe be careful when you talk to new parents. We're a force to be reckoned with. If I had listened to that neurologist, I would have never done any of this. So to end on a high note, this is our princess. She's happy.